Okay, good evening, everyone. Welcome to lecture number 2 of the Introduction to Machine Learning course. Lecture number 1 was just an organizational meeting where we practiced different things like, breakout sessions and generally talked about the syllabus and the course organization and so on. Those documents are all available for those of you who are registered. When you go to UB Learns in the information tab of UB Learns, you find the course organization, course syllabus.
Train, baby.
Yes. Okay. So we have, that's all we talked about in the first lecture. So today we actually begin our study of machine learning, and the course slides I use are all publicly available on my personal website. You just go to my homepage at UB, and down below you'll find Introduction to Machine Learning. If you click on that, you'll see all the course organization basically, and you'll see that is essentially the syllabus also. Sometimes I modify it a little bit, and so you'll see that, and you can even obtain the slides there. And so uh, the the first lecture we had the introduction to machine learning, what machine learning is about, and today I thought I would just launch into software frameworks for machine learning. It's a bit of a technical topic. It's not like broad things about, where all machine learning is used and so on. So it's a bit of a technical topic, but it covers a little bit of Python and how would you use Python to do a simple problem such as identifying all the vowels in a string of text. What would be the Python code for actually the first project is on logistic regression. Mihir is actually finalizing the description of the project. I understand it's going to be on logistic regression. I have a one-page code of logistic regression. I'll go over it with you, and you can take a look at it. I think it'll be useful for you because we want the first project to be on that very topic, and so we'll do that. It's kind of getting into the nitty gritty of coding in machine learning. I thought I'd do that, although most of the course is not like that. Most of the course is about all the algorithms, the theory, the linear algebra, the probability theory that goes with it, and so on. But you'll get a sense of it by looking at it, looking at a simple piece of code for doing the simplest machine learning program that for doing classification using logistic regression. So we will look at that today itself. And so you get a head start, particularly next Monday is no class because of Labor Day. You can get a head start. Mihir has already written up the first project, and I have to finalize it with him. And we will post it in the assignment section. You can get going on the first project as quickly as possible, particularly since you have some time over the 3-day weekend coming up. So that'll give you ample time to get that done. So I thought, let me start like that. Rather than this, I could have started with linear algebra. I could have started with probability theory. Okay, some of it you already know, but I was going to review those topics rather than use today's valuable session on the basics like that. I thought I would just look at the code right away, saying what does the code look like, and then get a head start, and then we'll come back to, well, how did you develop that code? So we're going to go kind of backwards like that. So that's my plan. So I'm going to all right, let's see. Are there any other chat comments coming in? Okay, none so far. All right, we'll do that. So if you want to raise your hand by sending a chat, please do that. All right. So now what I'm going to do is share the screen with. Okay. Okay, so this is the a page in UB Learns of course documents. So the slides on machine learning overview, that was the material last time. The slides are there already. And so today I was going to go over the second set of slides, which is ML software frameworks, machine learning software frameworks. And the attached files are 1.2. So the previous one was 1.1. This is 1.2, Python ML frameworks. All right. So that's what we will go over. Okay, Python and machine learning frameworks. Okay, so this is kind of a little nitty gritty, but I think it'll be valuable to you. Okay, what are we going to learn here? We'll talk a little bit about Python here. And there we will first look at a small piece of Python code for vowel counting, a simple one. You may want to try these out on your own just to get familiarized. And the second one is actually logistic regression in Python. Um, and so that'll give you a real head start on the first project, as I said. Mihir can jump in to see how it's going to be different in the first project than what I go over after we finish it. And we'll say a little bit about Python versus C++, and then we'll talk about machine learning frameworks such as PyTorch and Keras and TensorFlow and so on. So a little bit of this kind of a technical background rather than the theoretical and mathematical background. Machine learning involves four very significant components: lots of linear algebra, lots of probability theory, lots of algorithms, and lots of coding. And if you use GPUs and so on, there is even something about distributed computing there. So it brings all of these into one place. Um, and so we'll begin with Python. So what is Python? It's a widely used high-level general purpose interpreted dynamic programming language, right? It's interpreted as opposed to compiled. And the philosophy of Python was code readability. And it allows programmers to express concept with fewer lines of code than would be possible in languages such as C++ or Java. All right, so fewer lines. Okay, that sounds promising. So we can say, well, do the whole thing here, right? We can say, rather than having to code everything. So that's one nice thing. And something called Numpy, you will have to import that. Numpy is an extension to the Python programming language. It adds support for large multidimensional arrays and matrices, and a large library of high-level mathematical functions to operate on these arrays. Okay, so it's got ready-made mathematical functions. You know, why do we need these functions? One example of a function is sigmoid. Sigmoid is a particular mathematical function that takes any scalar input, converts into a value between 0 and 1. So it takes some real number as input and converts it into value 0 and 1. So uh, if it is a positive, for example, it's going to be 1, negative, it's going to be -1, or 0 and 1, right? Not -1, 0 and 1. So with some kind of a mapping like that. So sigmoid is a function. We'll just look at it soon. So the first one that I found, I know I was looking for some simple Python code, and the first one I found, I've given you the reference over here, and this was the task of vowel counting, is to count number of vowels in a string S. And it's a string of lowercase characters, and the program is to count the number of vowels in the string S. And what are vowels? These are the letters A, E, I, O, U. For example, if we have the string A, Z, C, B, O, B, O, B, E, G, G, H, A, K, L, your program should print number of vowels equal to 5 because it has got 5 vowels in it, I suppose. A, O, E, A, right? So those would all be the vowels. It counts them as vowels. Is that 5? 1, 2, 3, 4, 5. Yeah, there are 5 vowels. And the code is given next. So this is the Python code that they provided as an introduction to Python. So you may want to go over the syntax yourself and see whether this is readable, which is what Python is supposed to be. And there are comments here with the pound sign, the hash sign, I suppose. Variable s is predefined. Define the set of variable vol count to 0, vol count equal to 0. We're setting that. And then we have a loop here. If letter in S equals each vowel, increment vowel by 1. If letter equal to A, that's a comment, right? If letter in, and then if letter equal to A, vowel count equal to add, updated by 1. And if else, if elif letter equal to E, vowel count equal to update, letter equal to I, letter equal to O, letter equal to U. And comment is print the concatenated first string and vowel count. Print number of words plus str vowel count. So it prints this as a string. So you may want to just try out something. If you've never done coding in Python, you could do that. And of course, if you're very familiar with Python, then you know what I'm talking about. All right. So what I'm doing here is a little bit risky from the teaching point of view. I'm saying, okay, well, that was just a simple Python program to count the number of vowels in a string. How about we just look at a piece of machine learning code, and how does that look like in Python? And this is one of the favorites, or at least my favorite. For my favorite for machine learning is a simple algorithm called logistic regression. It's got a fancy name. It takes as input some x. All right, x is actually shown in, this is kind of symbols we use in linear algebra throughout in this course. If it appears in a bold letter x like this, it means it's a vector, or it could even be an array, it could even be a tensor, and so on. Let's assume it's just a vector, because then it comes in, what does it mean to multiply two vectors? So here we are doing W transpose X. W is a vector, X is a vector. So what it means is, supposing I have an X which consists of a string of values. So it could be an image which is scanned from, which is converted into a vector by going from top to bottom, left to right. You convert your input image. Let's say your own image on your phone is your X. So this W is a set of weights or numbers that are multiplying this X. We show it as W transpose X, in the sense, if X is a column vector, then W has to be appropriately, you want to convert it to scalar multiplication, so it's got to be appropriately a row vector. So normally in machine learning, we think of all vectors as column vectors. So we would have W transpose X would be to convert it into the transpose T stands for converting it into a row vector. And then now you can multiply the elements together, resulting in a scalar or a single number. So it says, here is the input image, your face, and your face is being multiplied by a set of numbers for every pixel in the image, and gets you a number. That number is converted by this sigma is a special function called the sigmoid function. This is a Greek symbol sigma, called the sigmoid function, which takes this as input and converts it into a value between 0 and 1. So what does the sigmoid function look like? Here's a picture. If supposing the input is Z or Z, then the sigmoid function has a particular form over here that goes from 0 here and 1 up here. It makes a conversion from 0 to 1. Sigma of Z is being converted by this particular function here. All right. Now we can add a bias to it, sigma W transpose X plus B, to move it around as to where it makes the transition and so on. So, so this is a very powerful algorithm Let's say the program that recognizes your face, right? We have, and a lot of us have phones which log you in by looking at your face, which means it's a 0-1 function. It says, yes, it's you, or 0, it's not you. There is this transition here between 0 to 1, slight value in between, but it's a pretty sharp transition here between 0 to 1. So it's a powerful program that simply takes as input X and multiplies it, applies a sigmoid and says, if it is 1, then you're in. If you're 0, it's out. For a biometric system, I suppose, for your face or your fingerprint or what have you, that itself. Now, the main issue is going to be, how do you know that W? What should be the value of W? That becomes the machine learning problem. Machine learning problem is to take a set of samples that are used for training and figure out what is this value. How do you weight all the pixels of the image of your face so that it is 1 or 0 based on how you have trained it. Okay, so that is what this is all about. Now, along the way, we'll introduce an idea. This is quite popular in machine learning, even in some of the software tools that you'll use. These are what are called as computational graphs. This is a computational graph that shows what is the computation that is needed. Computation is a simple one. Take the X, multiply it by W, and take the result and apply a function sigma to it, which converts it to value 0, 1. And how do we do that? Computational graph says, what are the steps in the computation? This X is not a scalar. It's not a single value. It's a vector. It consists of values x1, x2, x3, like that. Could be up to x million, because we might have a million pixel image. This one shows only 2 values of X, x1, x2. It also shows W1 and W2. So it's figuring out how much to weight each of these values. And then the operation between W1 and X1 is there's a multiplication symbol over here. That's W1, X1. And this is, again, this multiplication says W to X2. So we have 2 numbers. And we have an addition says, take this number, result of this number, and add them up. That's what a scalar multiplication is about. This is where the linear algebra comes in. W transpose X scalar multiplication is to multiply the corresponding elements of W and X, and then you add them all up. And so that is exactly what is happening here. And we take the result of this addition and send it to this node here. We call these as nodes. And nodes represent a computation. So this node, or a value, the value. There's nothing here but the values. And then here's a computation to give you a value. And so here is a computation to give you a value. So this computation is that of evaluating the sigmoid function shown over here. Well, that sigmoid function, hopefully, I mean, that can be implemented also. What is the sigmoid? How do you get this function? It has a formula is 1 over 1 plus e to the something, right? So that can be, you can write the code for sigma, or hopefully Python or Numpy already has that sigmoid available to you as a library function, and you could use that. I'm showing here one more graph for the same thing. This is what's called the depth 3 graph. There is 1, 2, 3, the 3 levels of computation going on before you get your result. That is X times W is the first one, and then adding each of them is the second one, and then applying the sigmoid is the third one. This is in a slightly refined language where it says, hey, don't bother doing vector multiplication and all that. I can already do that for you. And I can even compute the sigmoid for you. In which case, or it could even do logistic regression. It could do the whole thing for you. Just give me a W and an X. I'm going to compute sigmoid of W transpose X without having to do a 3 deep computational graph. I can do a 1 deep computational graph, which says, take a vector W, take a vector X, and give me logistic regression of that, which means compute sigmoid of W transpose X. This kind of also illustrates the concept of depth in what's called as a deep learning. In deep learning, we have levels of computation. So here we have 3 levels, here's 1 level. Well, what's the difference? In some higher level programming language, these are available. If you're going to be doing it in Python, you're going to be doing it in this way. And we're going to specify all this for your project one. I think for the simplest project, we want you to use basic functionality of Numpy and not use higher level functions, but we'll tell you that. And more generally, logistic regression is not just W transpose X, but W transpose X plus a bias B, which controls the nature of what you're converting, where you are in this. Okay, so W and B are now so we refer to W and B as the parameters of this network. And W is a vector. It's a whole bunch of values. And B is going to be a scalar value. We're going to add to W transpose X. So these are called the parameters of the network, W and B. So the machine learning problem then is, how do you determine that W and B from a whole bunch of training samples, which have been provided to us, saying for each value of X, is the answer 0 or is the answer 1? That kind of a data set we need. And we would take that and then learn those Ws. I suppose in these face recognition systems that the iPhone and I suppose the Android phones provide, they don't need that many examples, right? They just look at your face from a few angles and they're pretty good after that. But a lot must have gone in. That's only a few training samples to figure out it should be 0 or 1 to recognize you. But they would have used many large sample sets to figure out most of the values of W. I mean, the value of W, and simply modify it a little bit based on the particular individual that is owning now the phone, right? Kind of a thing. So anyway, let's not worry about those kinds of aspects. We are only interested in how do we implement this in Python. The code we're going to see is not just to implement these steps in Python to compute sigma of W transpose X. We will actually look at the machine learning code that figures out what should be the value of W and what should be the value of B. We'll actually look at the machine learning code. So the next slide is going to give you we need some math here. And the mathematics here is going to be, well, how are you going to figure out this W based on a set of training samples? It says, well, we are going to start with an arbitrary set of weights W. And as you present the samples to me, I will change the W and the B if it is wrong. And we will correct ourselves from this training set. And in order to do that, we do what's called as gradient descent. How much do you change the W by? You proceed in a direction. Should I increase the W value? There are so many W values, not just one. So we need to increase or decrease these W values in some direction. And that direction is to minimize what's called as a loss function. We have to bring that in. What is this loss function? Loss function is like make fewer mistakes. What should have been the value? The correct value should have been 1, and you have given the answer 0. What is the difference between them? And that is an error, and you're doing errors over a whole set of samples. It's not just one sample. I give you many samples, and over all of them, what was the error you committed, and you now change it appropriately. So go in a direction where the loss function is minimized. The loss is how wrong it was. So this involves defining a loss function, and it involves defining the derivative of the loss function with respect to W and B. So we're going to do derivatives of the variables here are W and B. We are trying to figure out what the W and B are. X is something that's given as input. W and B are the key things here. So we're going to define a loss function. And the particular loss function that we use for logistic regression is a well-known loss function, which is not the sum of squared errors. This is this is another loss function that we use, which we will encounter. We'll define that eventually. So we'll come up with a loss function. And it's called cross entropy, by the way. The name of the loss function we'll use is called cross entropy. And so we first define what is sigmoid function, the sigma function. What is this function mathematically, which takes an input z, converts into sigma of z, which you may not have to implement, but we'll look at it. If you had to implement it, that's what you'd have to do. And we will look at how do you define the loss function as cross entropy, and then how do you compute the derivative of the loss function with respect to w and b, and how do you use the value of the derivative. We take the derivative, and what do we do with the derivative? Derivative is like dy by dx, right? That's the kind of thing, derivative of the loss function. The function we're going to take the derivative of is not sigmoid, but the loss function, which is cross entropy. We take the derivative of that, and we take the derivative and we subtract it from the value of w. So we say, okay, you have some w you have, start changing w in some direction, and so that the loss is minimized. We do that typically using gradient descent rule, which is w gets changed to w minus some alpha of the derivative. Alpha is called the learning rate. How much do you change the w becomes a question. Do you change it by a lot or do you change it a little? So we do that in the gradient descent step. Now, to define the gradient of the loss function, we have to, of course, first define the loss function, which involves the correct answer and the answer that the system is giving. We need additional variables coming into the play. For some setting of w, let's say the output is y, but the correct value should have been, let's say, p. So we say, what's the difference between p and y? So we have to bring in these things like y and p into the picture, and we refer to this w transpose x as z or z. And we set up the equations, and the derivative turns out to need an application of the calculus chain rule. So we are going to have so many variables already. We have w, we have x, we have y, and we have p, and we have a z or z. I get confused with z and z. I was teaching this course, a version of this course in India last semester. There I had to say everything in as z or as z. I'm sorry, z. I'm back here in the US now. I have to say z now, right? So bear with me if I say z sometimes and z other times. And all right, so z is w transpose x. Okay, so next slide has got all these equations, and don't be baffled by it right away. And so the next slide is going to be all the equations that you need to implement logistic regression. That's the learning. So the next one is not just to compute w transpose x sigma. That we know how to do. We've already given it. We are now going to have, what does it take for the machine to learn w and b? And that is where we need all these equations. And the slide after that is going to be the Python code, the machine learning code to do that. And your first project is to implement this, okay? And Mihir is going to tell you about what kind of data set you're going to have. Okay, was there a question? See, when I go into this slide share mode, I cannot see the chat box. So Mihir, you can bring it up if necessary, okay? All right. All right, bear with me. This is not to confuse you and throw you off. It's actually a fun slide if you look at it. It's got all the mathematics you need, and it tells you what is all the kind of mathematics you need to review. And let's go one by one. Learning task of logistic regression. All right, the first thing it says what about, we are going to need the sigmoid function, right? We just saw what it looks like. We need the sigmoid function to produce a value between 0 and 1. And in Python, it can be done. Is define sigmoid of z, return 1/1 plus numpy. It's 1 over, basically it is the equation shown in this box. It is 1 over 1 plus e to the power of minus z, all right? That is g of z. And that is this function that is shown over here. So that's what sigmoid is computing. So 1 over 1 plus e to the minus z has a plot that looks like that, right? And what is going to be the z? What are you going to be inputting is going to be w transpose x plus b, which we just saw in the previous slide. And the prediction, that's why P for prediction is a value between 0 and 1. Between 0 and 1, but that is defined by sigmoid of z. So if we take sigmoid of w transpose b, which is actually z, we get the prediction. So this is the implementation of the decision part. That is, once you know what is the value of w, what is the value of b, this is how you're going to get the sigmoid function implemented. So I mentioned in the previous slide, we're going to need a loss function. Sometimes in machine learning, we hear the word loss function. Sometimes we hear the word cost function. Is there any difference between the two? Typically, we think of it as the same thing, but here is a fine-grained definition of difference between loss and cost. Loss function is the loss for a single training example. And cost is the loss for the whole training set. So you can say the loss is computed not just for one training sample, but all of them together. If there are 5 shots that were taken of your face by the authentication system, then you would have a loss computed over all those. Is it getting it right? So this loss function is a function of P and Y. What are P and Y? Y is just the output of the system. Y is the P is our prediction and Y is the correct value. Okay, these are the two things. P is a prediction. Our prediction says it's 1 or 0, but the correct value is what's given by Y. And how is this loss function defined? It's got a peculiar form. It says minus Y log P plus 1 minus Y times log of 1 minus P. All right, is that something you have seen before? It looks a bit like the entropy function, if you have encountered it anywhere. Entropy function is minus pi log pi, if you remember. It is summation over all the values of y. That is the entropy of a probability distribution. Here we have values p and y. We are kind of stating it probabilistically. We are talking about a value between 0 and 1. That sounds like a probability. And so this can be treated like we're talking about a probability associated. Y presumably will be either 0 or 1. Yes or no? P is some value between 0 and 1, a real number between 0 and 1. And we're trying to make that come close to 0 and 1, but it could be some value in between 0 and 1 also. So we define, and why do we define the loss function like this becomes a question. And we'll look at that some point later. So we'll derive that is a good loss function. Sometimes you use sum of squared errors as a loss function. That is, you simply add up how many errors you've got. It turns out that is not as good a loss function in certain situations as this one. So we have this loss function. So the goal is to choose. Now you say this, it involves P and Y. And what is P? P is sigma of Z. That is the prediction of the system. So P depends on Z here. And what does Z? Z depends on W and B and the input X. So there is some dependency between all these things. P depends on all these other items. So we are going to try to minimize this quantity. And we want to find the values of W and B that are going to minimize this quantity. And so how do we relate this quantity? How do we take the derivative with respect to W and B? And there is all these other variables involved. So this set of equations below, they're not rocket science here. It is basic calculus. So let's be bold and look at what these are. So this says updating the weights, and we refer to the W as the weights. There are so many weights, and there is a B as the bias. All right, there's only one scalar value here, and so in any machine learning algorithm, we typically start out with, let's assume W and B are some values we already know, right? We modify it. I suppose that's exactly how the iPhone face recognition system would do. It already knows a value of W and B. When you buy the phone, they've already programmed in the W and B. It just needs to modify the W and B based on the owner of the phone a little bit. And how does it modify it? That's what's given by gradient descent. It says B is changed to B minus alpha dB, and W is changed to W minus alpha dW. And what is this dB and dW? Alpha is a learning rate. It is simply saying how much of a change you want to make on the B. You want to make a lot or it's only a little bit. And that is the learning rate. If you make too much of a change, it can overjump or it can overshoot where you're trying to change it to. So a small value of alpha is going to take some longer time to change it. So what is this dB and dW? dB is defined as derivative of the loss function with respect to B. So we're saying this is a partial derivative. Derivative of LPY defined over here with respect to B. And then what is this dW? dW is derivative of this loss function with respect to W, and we call it dW. So we need to compute the derivative of the loss function. And once you have done it, you can change the B and the W, and you're moved one step closer to the final value. We need to keep on doing this over repeated learning, which got to be done over what are called as epochs. How many times do you have to look at all the examples? That's a different question, but this is how we update it. Now we set about all the equations in all of these boxes. In all of these boxes is about how do I compute this derivative of LPY with respect to B. And we use finding dB and dW using chain rule. So you may remember chain rule of calculus. So dy by dx, for example, can be written as dy by dz times dz by dx, right? That's the chain rule of calculus. We do that when we have several variables intervening. Particularly, we have these computational graph, we have functions of functions going on. That is, we first add, and then the result of the add to that we do multiplication, and the result of that we do sigmoid. So this is what are called as compositions of functions. And chain rule is the tool to calculate the derivative of an output in terms of the inputs, where there are some intervening values. Clearly, there are intervening values here when you compute derivative with respect to W of this quantity. This quantity involves P, and P is in terms of Z, and Z is in terms of W and B, and so on. So that is where the chain rule has to come into play. So we are going to compute derivative with respect to P, which leads to computing the derivative with respect to Z, which leads to computing the derivative with respect to B. What we are really after is computing the derivative with respect to B. That is what's going to be used to change the values of B and W. So this math, you have to have a little patience now to look at these boxes. The first box here, I'm just reminding you what is d by dx of log mx is. That is basic calculus, right? If I'm computing the derivative of log mx, what is the answer to that? Derivative of log mx can be written as the derivative of mx in the numerator divided by mx. That's because of the log function. That is the derivative of mx with respect to x is only m, denominator is mx. So that's equal to 1 over x. Okay. So derivative of log x is also is equal to 1 over x. Derivative of log mx is also 1 over x. Where did that coming? Okay, because we have logs over here. So we need to know something about derivative. How do you take a derivative of log, right? So that tells us let's say we are trying to compute the derivative of this quantity, not with respect to B or W, but let's say we want to compute the derivative with respect to P, which we know here. There's a P explicitly appearing here. There's no B and W here, but there's a P here. So what does the partial derivative of that loss function with respect to p look like? It says that's going to be derivative of the first term and the derivative of the second term, and then so we have to supplement this equation over here. So that leads us to say that the derivative of L with respect to P has two terms, difference of two terms, 1 minus y over 1 minus P minus y over P. All right. So we are just computing the derivative of this quantity using this rule about what is the derivative of log. So that's how we get the derivative with respect to P. Well, what good is derivative with respect to P? We're going to use that to compute the derivative with respect to Z. So what is the derivative of this quantity with respect to Z? There's no Z over here at all. Well, that says chain rule. It says derivative with respect to of Z is equal to derivative with respect to P times derivative of P with respect to Z. So that is dy by dx is equal to d y by dz times dz. That's what we're using here as chain rule. And since we already know the derivative with respect to P, we have computed over here, we can plug that in, and we are now going to get this quantity here, derivative of P with respect to X. Since we know what P is, that is sigmoid, we need to know what the derivative function of sigmoid looks like. We are plugging that in here to get this expression. Derivative with respect to P is P minus Y. Wow. That's interesting. What is P minus Y? It is simply take what is the algorithm outputting and what should be the correct value. Simply take the difference between the two as a derivative. A lot of the machine learning is like that. Just take a look at the output and take the difference between the input, and that's your derivative. The difference is the derivative. That's what we're getting over here with this loss function. So we have now come up with the derivative of this loss function with respect to Z. But what we are really after is a derivative with respect to B, and we are after a derivative with respect to W. That's what we want, right? So this says if you are looking for derivative of L with respect to B, then I can write it using chain rule as derivative with respect to Z times dz by dp. And this quantity, derivative with respect to Z, is dz here, denoted dz. And here is the derivative of the rest of this with respect to B. So this is the term we refer to as dB over here. And then what we are doing is we are summing over all the samples. So this says it's not just Z, but summed over all the training samples, average over all of them. And the derivative of this quantity just turns out to be 1. D by dB of W transpose X plus B is just equal to 1, because W transpose is independent of B, and then dB by dB is equal to 1. So that's just 1 over here. So that's why it just becomes dz. So this says the derivative with respect to B is this quantity. And what is this quantity dz is something we have computed earlier on, okay? And okay, so this is dz over all the samples. Similarly, derivative with respect to W is computed as simply times dz over t. All right, so this is this is the total final set of equations that you need to implement it. So the dz is nothing but derivative of LPY with respect to Z. That is this quantity, is this dz. Okay.
Professor, there are 5 to
Well,
6.
that is exactly here. That is P minus Y. Derivative of L with respect to Z is P minus Y is this quantity. So this is saying, take all the P minus, so you got M samples, take the differences among all your N samples, add them all up, divide by the total number. Oh, that is simple enough. So that is a very simple expression for the derivative. And this is saying, take all your outputs, compare it to what should have been the output, take the differences between all of them, add them all up. That's the value of your derivative of the loss function. And you add that up. Okay, so that is the overall. Mihir, you wanted to add something. Go ahead.
There are 5 to 6 questions in the chat box.
Okay.
The first question is by Gaurav. Is loss function the same as error?
Okay. Um, yeah, I've used the word loss, I've used the word cost, but I did not use the word error. Uh, one loss function is very popular, is called the sum of squared errors. Sum of squared errors is how wrong is the output. So error is the measure of how wrong is the output. So if it is a real value as the output, one method we're going to look at is called linear regression. It is a continuous value rather than a value 0, 1 discrete value. In linear regression, we are outputting a continuous value. So if the output was supposed to be 5 and the output produced is 3, you say, what is the difference between 5 and 3? Okay, the difference is 2. And we square that and say, okay, square of 2 is 4. So that's called squared error. So if I have a whole bunch of examples that the output is wrong by a certain amount, we take every one of the wrong values. We take the differences, add them all up, and we square them all up, add them up. The reason we do squaring is sometimes the loss can be either direction. Sometimes it can be positive, sometimes it can be negative. We eliminate that part and we simply take the squared value, add them up. That is called sum of squares error. So that is the error, and the objective of the machine learning program would be to minimize the sum of squared errors. So when you say error, it becomes an issue of how do you measure error, all right? So sometimes the loss function is the squared error function, right? It's one particular loss function. In this case, we are not using that. We are using this strange thing called cross entropy. Again, it's a measure between P and Y. P is the prediction, Y is the correct value. How do you relate P and Y? In this strange way. The value is between 0 and 1. So we do y log p, 1 minus y times log 1 minus p. So this is the loss function here. It is also, you can think of it as some measure of error, but it's not explicitly so. And cost is taking the summation of the loss over a whole set of training samples, just like we talked about sum of squared errors. All right, so that's the answer to the error question. All right, what's the next question?
Um, in the case where we are updating the weights, we have a term which is alpha. Is the alpha term being updated as well?
Okay, very good question. Who asked this question?
This question was asked by Arghya Datta.
Okay, very good. Yeah, yeah. Please give them. I want to get to know you, and I'm thrilled when you participate by asking questions. I hope I can answer them. That's all. All right. So the question is alpha also being updated? Alpha is the learning rate. So it is. There are what are called as the hyperparameters in machine learning. We simply say, okay, we're going to tell you it's going to be 0.1. How do you know 0.1? Well, it's based on practice and say, look, we're going to update it at a certain rate. That's why it's called learning rate. If we change B too much, you're going to be jumping around the minimum. You see, I have a diagram here that shows this is the cost here. The cost function is being plotted with respect to W here for a given set of weights. And we would be, the cost will be somewhere at this point, arbitrary value. The goal is to keep on moving until you get the lowest value for the cost. So the cost or the loss, you can think of loss for one sample, cost is for a lot of them. So we can change from this value to this value to this value. If you make this alpha very big, it might jump over the minimum and go from this side to that side. And then from when you're here, it'll jump from this side to this side. It'll zigzag all over the place. And so alpha cannot be very big. If you make alpha very small, it is going to make some infinitesimal small changes. And our goal is to take it as close as possible to the minimum as possible here. So alpha is fixed. So then comes the question, well, how do you know its alpha is 0.1? Why not 0.2 or that is another topic, how to learn the hyperparameters. So there are methods of choosing these rates and so on. So let's not worry about it immediately, because that is we can take it as a hyperparameter that is not learned from the data It is maybe create another data set for that or something, and you get it from outside. This is called them hyperparameters, which are not W and B are parameters. Alpha is a hyperparameter. Okay, so good question. Okay, next question.
Um, so there's one more question. How do you get to dp by dz, which is the derivative of the predicted value
Yeah,
uh,
yeah.
versus the value of z?
DP. How do you get DP by DZ? Right, DZ.
Yes,
Okay, who asked the question?
it was again asked by Gaurav.
Gaurav. Okay, Gaurav, thanks for participating. All right, DP by DZ equation is right here in this box. Okay, can you see my arrow moving around? Can you see that? Yeah. So dP by dz is equal to P minus Y. Oh, right. Yeah, okay, let's say dP by dz is P times 1 minus P, and that is what's being plugged in to get, okay, dl by dz is P minus Y. All right, so we needed dP by dz. How do you get that? dP by dz is, it says because of the sigmoid function. So because the sigmoid function says that the derivative of P with respect to Z is nothing but sigma times 1 minus sigma, right? How do you get that? Well, if supposing I define the function like this, 1 plus 1 over e to the minus z, and we're taking derivative, that's what the sigmoid function is. So we want to take the derivative of that, and that you can show by simple rules of calculus. It is nothing but sigma times 1 minus sigma. All right, so take it as a simple calculus exercise. So given this function p, what is the derivative of p with respect to z? It is nothing but the value of the sigmoid times 1 minus sigma throughout. That's the value of the derivative. Okay, so that's what's being plugged in here. Okay, good question.
Thank you, Professor.
That involves a little bit of calculus about derivative of sigmoid. Okay, yeah, next question.
Um, the next question is by Yosef. The question is regarding the learning rate alpha.
Yeah.
Does it depend on the size of the training data set?
Uh-huh. Okay, good question. Does it depend on the kind of data set? I would say no. It is something fixed by the machine learning programmer uh, based on experience with machine learning, and it is not a function of the data set. That's an interesting question. Whether well, it does. It does to some extent. If you have a huge training set and you have a very small value of alpha, you're going to be moving very, very slowly because you have to run through all the samples uh, by computing. This M is very large, right? This M is very large. And so there are a lot of terms over all the samples you're calculating this quantity. So the computing the dB is taking a lot of effort. So, so if you have a very small alpha, it is compounding it, and it becomes extremely small. And so that's an interesting relationship. I haven't seen that before as to how you would control alpha based on the training set, but we don't think of it as any kind of dependency between that. It's just a question of slowness of convergence. Okay. All right. Good question. All right.
Um, then there are some questions regarding the implementation, if all these functions are implementable with NumPy libraries or not.
Okay. My next slide actually gives you the entire code for this, all right, in Python. And this is what I think this particular website gave this to me, and that's where I got this code. You may want to go over that and get ready with it, implement it yourself. You know, implement this code and play around with it. Only thing is you need a data set to do this, right? You need to do this on a training set with the correct values and so on. What is the value of X and what is the value associated with it is Y, right? You need X and Y values. That's called a supervised training set you need. Once you've got a true supervised training set, you can do that. And Mihir is going to give that to you for the first project. And but you can also, I think this site tells you where to get some data sets. So here is the logistic regression code in Python. All right. So you may want to study it on your own. So they said there is a site called scikit-learn to create a data set. And from the data set, you can do all these things. They're all Python code over here. Look at this one, define sigmoid of Z. So they went about defining it from scratch. Return 1 over 1 plus NP exponential. That is the definition of the sigmoid function. And there is the rest of it. There is Z equal to W transpose X, right? There it is. W transpose X plus B comes here. P is sigmoid of Z. Cost is again given in terms of the cross entropy function we just saw. And then there is some kind of a summation might be going on over here. dz is p minus y. That's what we said earlier on. dw, db are being computed. And w is being updated by w minus learning rate times dw. B is updated by b minus learning rate times b. And then there is a plot also for plotting the loss function as you move along. And from the code above, you find P, it will be between 0 and 1. And so you'll have to do this over several epochs where you're presenting the samples again. And because what's happening is you're going to be moving down and down and down. So you have to keep presenting the data again and again until you come to a point where we are not changing much. So that is somehow a test that is incorporated. Let's see, number of samples equal to 500. There are a few other parameters come into play. And Mihir, you want to add anything more? Because you are the one most familiar with this code in some form, maybe in a different form.
Yeah, this code is exactly what they have to implement using Python. Although some of the functions here might be pseudocode, you might have to implement them something like importing the data set first and using that particular data set for actually implementing the logistic regression on top of it.
Okay, great. So we have given you the code and that's first project, right? So you may have to make some changes in it and so on, but on the data set and so on, there'll be some issues preparing the data for inputting and all that. But the basic code is this, and the previous slide gave you all the mathematical equations, which might ignite your mind to go and say, okay, how did you get that? Where is the calculus here, which is all the derivatives? And also about what is this loss function? How did that come in and all that kind of stuff, right? Okay, I thought this is the best way to start you guys off rather than starting about what is a vector and what's a scalar and all that type of thing, okay? Very good. Any other questions, Mihir?
So there's a question, what are epochs and what exactly is an epoch?
You want to answer that?
Yes. Epochs is basically when you are looping over your data set once. That's one epoch. That means you're going over all the instances in your data once. That is one epoch. When you do it multiple times, that means you're making multiple iterations over the entire data set. Epochs is a hyperparameter again. You might set it to how much ever you want in the first when you start, and based on your epochs versus training loss, you will set the value of epoch.
Okay, I noticed just now when I was looking at this code here, epochs equal to 1000, learning rate equal to 0.01. I said 0.1 earlier on, 0.01. Okay, all right. Any other questions?
Then there are very specific questions regarding the code, which we can answer maybe in the office hours.
Okay, all right, fine. Okay, good. All right, so that was good questions and hopefully that was helpful. All right, so I just threw this in right away saying this is what machine learning looks like, all right? And Of course, we're going to be learning several algorithms. This is for logistic regression. We are going to be looking at linear regression, where the value is not 0 or 1, but a continuous value. You're predicting some value, and it's got a simpler form. And sometimes some machine learning problems have closed form solutions for W and B. Linear regression is one of those problems. There's a closed form solution. This is not a closed form solution for W and B. This involved an iterative solution which starts with some value and you keep on modifying it. It's an iterative solution to the problem because there is no closed form solution to logistic regression. Linear regression does have a closed form solution, but even there, the closed form solution may not be satisfactory because it involves inverting a matrix, and which could be singular matrix, which means the inverse does not exist and that kind of thing. So there also an iterative solution is possible. And we will move from logistic regression afterwards to neural networks, which have the same flavor. You see the calculus here is going to be kind of similar throughout the semester. We got a gradient descent step, and we got the derivative step, which involves a chain rule of calculus. We need to have a loss function, so on. So it's kind of repeated again and again, but with more complicated structures, which leads to neural networks, which eventually leads to deep networks and so deep learning and so on. But this is the basics of it, okay? All right, then I have a couple more pieces of code for you to play around with. If that was a little more complicated, we went from the first piece of Python code that I went over was to determine how many vowels are there. And the second one I jumped into was a little bit more complicated, which was logistic regression, learning logistic regression parameters. This one is something in between. It's FizzBuzz. And I was just looking at, what are the pluses and minuses of C++ and say Python. And this is comparing the code in C++ to the code in Python for a slightly different task. It's for the FizzBuzz task. It's a children's game who have to who go around, saying numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 like that, and take turns giving the next number. But they have to say fizz if the number is divisible by 3, and if they have to say buzz if the number is divisible by 5. And if it is divisible by both 3 and 5, they have to say fizz buzz, right? Like it's 1, 2, fizz, 4, buzz, fizz, 7, 8, fizz, buzz. And then when we get to 15, we got to say fizz buzz like that, right? So that's fizz buzz. So it says print I equal to 1 to 100, except if divisible by 3, print fizz. If divisible by 5, print buzz. Divisible by both 3 and 5, print fizz buzz. The code looks like this in C++. That there is the if else statements, and there is all this code over here. It looks a little bit messy over here. And it's first it's checking to see if it is divisible by 3 and 5. And then it is fizz buzz. If it is divisible by 3, it's fizz. If it is divisible by 5, it's buzz. And then so this is the code for fizz buzz. The Python code is a little more readable, as you can see. If I equal to 0, continue. Else if I divisible by 15, 0, print fizz buzz. Else if divisible by 5, print buzz. You're checking the remainder each time here. And so this code in Python is more readable than this code in C++. And so we say Python is an interpreted language, emphasizes code readability, fewer lines of code than C++ or Java. So Python, this is all some arguments as to why Python is so popular in these domains. And then Numpy is an extension of Python, library of functions to operate on arrays. And then there are all these machine learning frameworks which offer building blocks for designing, training, and validating deep neural networks. You can think of logistic regression as the very first step to build neural networks. We only have one value that's computed using W transpose B. If you do that over several different inputs and weights, put it all together in some kind of network, it becomes a neural network. But the training is all very similar. And so that's why we say validating deep neural networks through a high-level programming interface. And these are optimized for performance and provide parallelization for implementation on GPUs. So when you go to a machine learning framework, the parallelization and all is done for you. And there are also visualization and modeling and interface. So what are all these frameworks? There is a whole bunch to choose from. And this one is getting a bit old in 2017, about 3 years old. What's happening is some consolidation is happening. Facebook was took another framework called Torch and came up with PyTorch, and then here we have Google, who have TensorFlow and an easier to use Keras. There was something called Theano, which was done in a university. Some of these are being abandoned, which were in universities because of the support and all that. So what began in universities for Theano, Torch, and so on, but it's all consolidated into TensorFlow and Keras and PyTorch. These are the Seattle companies, which is Amazon and Microsoft, and so they had a machine learning framework called Gluon. I don't know how widely it's being used. Maybe I need to update this slide with what's exactly happening today on that. So what are the differences on these frameworks?
Professor,
Yeah.
we have a mock quiz now for the last
Oh,
10 minutes.
all right. We are into last 10. Okay, fine. I'm going to skip this part. You guys can look at this. There's no quiz on Monday, but yeah, we plan to have our quizzes every Monday, but Mihir is going to run a mock quiz now. This is not a real quiz. I guess I'm not even sure the questions are technical, or are they not?
Um,
They are technical.
so there are some questions which are technical,
Yeah.
and there are some questions which do not require any,
Yeah.
just some dummy questions.
Fantastic. Okay, fine. So this is a trial quiz. So follow the guidelines. I think we're going to do it on UB Learns. Is that right?
Yes, so everyone just open up your UB Learns account, open the course, and on your left, there are options, and you'll be seeing quizzes. Under the quizzes section, just you'll find the mock quiz.
Okay. So Mihir, you'll
Um,
take it from here, right? I will quit on this. Okay.
okay, Professor.
Yeah. Okay. You guys enjoy the mock quiz. This is for you to learn how to do a quiz. Okay.
Okay, is everyone able to see the mock quiz under the quizzes section on UB Learns? Okay, cool. You have 15 minutes to solve 7 questions. If it were a normal quiz, we would have almost